Imagine standing in a massive room packed floor to ceiling with loose pieces of paper. Millions of pages are blowing around, stacked in random piles. In an environment like this, finding one specific person's record would take you years. Compare that physical nightmare to a modern computer system. It can sift through millions of records and find the exact person you are looking for in a few milliseconds. To achieve that kind of speed, computers use a database, a highly organized digital library. Inside this library, you have tables. You can think of a table as a single filing cabinet dedicated to one specific subject, like a roster of students. Open a drawer in that cabinet and you find a standardized blank form. This form dictates the columns. Columns are the required categories of information every single person must provide, like name, age, and major. When you fill out that form with a specific student's details, it becomes a row. A row is one complete individual record representing a single person or item, and it tucks neatly into the cabinet. Data on its own is just raw, scattered information. A database provides the predictable architecture necessary to turn that information into something useful. To ask this digital library for information, we use SQL, Structured Query Language. It is a standardized set of commands that reads very much like plain English. We are going to build a simple SQL request. To understand how it works, we will build it in the exact logical sequence the computer uses to process it. The computer first needs to know where to look. We give it that starting point by typing from students. This tells the system to walk past all the other cabinets in the library and pull out the specific table holding student records. Identifying the correct source table is the absolute foundation of every data request. Without that from instruction, the database remains idle. Our students cabinet might contain tens of thousands of rows. If we pull all of them, we are right back to a chaotic pile of information. We need to isolate only the records we actually care about. We do this by applying a condition using the where command. We can use basic math to set the rules. So we add where age is greater than 20. Instantly, the database checks every single folder against this rule, keeping the matches and discarding the ones that don't match. This where condition acts as a precision filter. It prevents information overload by returning only the specific records that fit your criteria. At this point, we have the right folders, but those folders still contain every single column of information, their ages, majors, addresses, and phone numbers. We might only need one of those details. We apply our final instruction to format the output. By typing select name, we dictate exactly which columns should actually be displayed. The extra categories fold away, leaving us with a perfectly clean list of just the names. When we look at the complete request, select name from students, where age is greater than 20, we can see how the structure works. It is intuitive enough for a person to read out loud, yet rigidly structured enough to command a machine. Notice how humans write the instructions top to bottom, select, from, where. But the database executes them based on its own physical logic, first locating the table, then filtering rows, and finally picking the columns. At this very second, these exact commands are running the global internet. Every time you visit an online store and look for sneakers, you interact with a database. Selecting a specific shoe size and color on the website's menu is a graphical way of writing a where condition. The website translates your clicks into an SQL query to filter the store's inventory table. Every digital search works through this structured dialogue. SQL provides a reliable way to speak to a perfectly organized librarian and get exactly what you need.